Hello, I'm Sumi Her from Jeonnam National University in South Korea. In this lecture, I will explain the basic concept of machine learning and how this emerging technique can be applied to solve problems in polymer science. Okay, let's think about this polymerization-induced self-assembly as a system with input of polymer design and process variables and output of a types of self-assembly structure. So as you learned in the earlier two lectures, the selection of monomers and their sequences, or the overall composition and the polymer lengths, are very crucial to determine what is the output aggregated micelle structure. At the same time, the detailed method of this polymerization, in situ polymerization method, and how the samples are prepared and where this polymerization is occurring, all these detailed conditions are also very important to relating these final output structures. So think about there's a forward model which describe how these input variables and the output variables are related. And this model would be extremely complicated and very nonlinear. However, for some way, if one can find out this forward model, it can be very powerful to use to predict the resulting nano-object structure for a given polymer and the process conditions. And furthermore, if one can convert this forward model into an inverse model, then we set up a certain targeting structure as an input. Then the output of this model is going to be what kind of polymer and the process has to be used. So this would help to find out a novel structure and designing this related the polymer and process designs. So the paradigm on how determine this forward and inverse model and design new material and process has been changed. The first paradigm is based on experiments. Experiments on various input values are conducted and the data are collected to understand this forward relation. However, this approach cannot provide full understanding on the whole system. So the material design has to be based on try and error. In the second paradigm, these theoretical knowledges are applied to relate the system input and output. And as computational models in various lengths and time scales gets available, theory and simulations help to set a forward model, but mostly it's under certain hypotheses or assumptions, and the model is limited on some local interpretations only, rather than this full understanding as a whole. So nowadays, this machine learning has become more effective and gets more widely available. This data-driven science has attracted huge attentions. And today's lecture is about this most recent paradigm, where we are and where we are heading to. So in the first part of the lecture, I will provide the introduction on machine learning. So I will explain the basic terminologies and key concepts used in machine learning. Then I will move on and focus on how the machine learning is applied in polymer science. So three main applications on characterization, prediction, and inverse design will be explained. Then I will show what kind of challenges that we are facing now, and discuss and introduce some of the efforts to overcoming these issues. Okay, let's just start from what machine learning is. So think about there's some given task, such as recognition, tell whether it's a cat or a dog from the photo, and riding a bike, or prediction like whether it's going to rain or not by just looking at the sky. It's just like there's a certain given task. However, for the given task, how human and machine perform those tasks are very different. Machine performs tasks only based on explicitly programmed algorithms. However, in humans' case, we learn from our experience. So at the beginning, we have when we don't have any experience and knowledge, we cannot perform the task. But by repeating task, the performance gets improved via learning process. Now think about this machining. When the more complicated, advanced task has to be given to a machine, then it is going to be very challenging for human to manually create all the needed algorithms, because it's going to get more and more complicated. So the core concept in machine learning is make this machine can learn from the data, so the machine can improve or develop the algorithm and perform this sets of the task better and better. Actually, machine learning is not that new. So this classical machine learning include all the techniques from data mining and predictive analytics, which you might hold of, so such as regression, decision tree, and like a k-mean clustering and support vector machine, and etc. So in this classical machine learning, there are some human inputs. Humans still guide the machine what kind of feature to look at, and what kind of algorithm which will be trained has to be used, and etc. So because of that, it needs less data set compared to the deep learning. But at the same time, the human error can make this machine make a wrong decision, like a poorer decision with low accuracy, and etc. So however, this deep learning is more flexible, and making this artificial neural network, so without any given human input of this, it automatically finds what kind of feature to look at, and everything is more result driven and complete as itself. Development in this learning algorithm and availability of these big data sets and this low-cost computation makes this huge progress in this machine learning field. And now this machine learning application can be found everywhere in your life, like a Netflix make this personalized recommendation for you that also uses machine learning. And all this something like businesses, science, and engineering, so you can find this application everywhere. So there's this AlphaFold 2 is the deep learning network by DeepMind's company. What they can do is this AlphaFold 2 can predict this three-dimensional protein folding structure with unprecedented accuracies. So which was a very big challenging problem in this structural biology field. And they, based on this protein data bank, using this number of the data set, now they announced this one, and now it can predict almost nearly every protein in the human body, and as well as other yeast, fruit flies, mice, and more. So it's a very sensational outcome of this development in this field. So deep learning tries to mimic humans' nervous system. So it has this interconnected network structure, and the basic building blocks of this network is called perceptron. And this perceptron is a mathematical model of this biological neuron, this neuron which process and transmit information through electrical and chemical signals. So this neuron receives multiple signals from other neurons via its dendrite, and then these signals are combined in the soma, and this combination is propagated via this exciton, and this new signal is fired off from this neuron to the another neurons. So this perceptron works very similarly. It receives these multiple input signals, and this combined and activated signal is passed to the next layers. So mathematically, this layered structure can describe any mathematical functions. So of course, when the function gets more complicated, we may need more deeper layers, many layers, and many of the perceptrons per each layers. But theoretically, it makes any function can be modeled using this network structure. And here comes the flexibility and the beauty of deep learning comes. So the very first, the simplest neural network model is this deep neural network. So people name this deep because when we have multiple hidden layers, people say it gets deeper and deeper. So this fully connected neural network can take any kind of the input and the output. So it reveals this complicated mathematical model between the input and output. So one example shown here is if someone wants to predict the home price, then there could be many inputs like a design and garden and security and everything, and receiving all these many inputs, and then it can predict the home price. But of course, to have this network can perform that prediction, you might need to construct this network, that model. And how this network is describing that model is, for each network structure, each line is how this is the signal from this node can be transferred to another node. So the weights per each line has to be trained, and this, depending on this weight, this whole network can describe a different kind of mathematical models. So when people say the training the network means for a given structure, this network from the given data set of the input and output, one is finding all these the weight functions for each connected lines. So in the earlier slides, the input is a one-dimensional, like high-dimensional vector. But in CNN, this convolutional neural network, the input has this two-dimensional format. So then this 2D data set takes this convolution. So you can see this small box is shifting and make the convolution, and this convoluted data set is passed to the next layers. And so using this one can have the feature extraction in 2D images more easily. So this CNN is widely used for most of these image-based works. So another important neural network is recurrent neural network. So in the application of this speech recognition or language translation, what is important is the input, instead of the input as a whole, the sequence of this input data is very important. So instead of putting this whole input sequence as a whole at one time, this input is plugged into the sequentially, and the information from the previous input value is passing to the next one, and that's how all the sequence data can be treated. DNN, CNN, RNN, these three important networks that I just mentioned is basically supervised learning, which means to train the network again to get the weight values for all these lines. This one is trained for the given data, which has input and true labeled Y values. So plug in these X values, and then for the initial weight values, that it gives some there's some output, predicted output, and there's an error that you have, you can compare with this true label. And based on error, you keep updating, optimizing this weight values in the network, and we call it that process as learning process. However, there's the different types of the network which named unsupervised learning. So it doesn't have answer label. So in this unsupervised level, we only have the input X only, and many of these, so not the deep learning, in the classical machine learning, so some of this clustering is one of the good example of this unsupervised learning. And this in the deep learning, these generative models are types of the unsupervised learning. So you've probably seen, so some of the images are plugged in, and there's a network which can generate something very similar. So we call those are generative models, and there's like a variational autoencoder or the generative adversary network. The GAN networks are the famous types of this generative model, and in this case, we don't need any true labeled values to train these networks. Okay, so learning means finding these weight values which are connecting its nodes in such a way to minimize the error, which is the difference between the predicted output and true labeled Y values. So that means this learning is basically optimization, right? And all this numerical optimization approach can be combined. It can be related to this training process. But here, in the deep learning, what makes this deep learning process more efficient is the concept of backpropagation. So think about, you want to optimize this weight value in this connecting the input and first layers, and you need this derivative of error over these weight values. But this value is all affected by the values in the next layers, right? Same thing, if you want to calculate this one, it's all affected by the values in the next layers. Same thing. So the way how we calculate this one is, again, I mean, here I just dropped out the other summations, just showing this one cases. But this, to calculate this one, you may need this value between these and this by the chain rules. So in the backpropagation, you calculate the derivative at the last stage first and store it. And to calculate the one in the next layer, we use all this pre-calculated and loaded saved data, and then all this value is evaluated based on this derivative at the last stage. And then again, once you have all the data stored up to here, and then those values will be used to get the weights in the earlier layers. So that is called the backpropagation. And again, this one makes this learning process much faster and numerically very efficient. So how this derivative is used and finding this optimal value, there's a lot of different kind of this numerical optimization scheme. The easiest one is gradient descent, but there can be the stochastic gradient descent, and depending on the when you choose the direction instead of the steepest gradient, you can also use the gradient in the previous step. So using some momentum, the history, so you can control the directions, and also you can control the step size, this alpha. So you choose the larger step size for the area you haven't explored, and then if you already have some more information, you can take a more conservative step size and etc. So combining those, there's a various kinds of the optimization method, and Adams method is the most widely used one. So when you are the first user of your when it's your first time, and then in there some the selection part of the optimizer, you probably want to start with the Adams method. So you can find many open source shared the deep learning libraries, and most of those, the famous ones, are based on Python. So you probably heard TensorFlow and PyTorch and etc. And of course, there's a Java based, and even the MATLAB has the deep learning libraries these days. So you can more easily access to these deep learning programs. And all these deep learning libraries this computation is based on the GPU, because GPU can conduct simple and many repeated computation more easily. So all these are based on the GPU computation using the CUDA libraries. Okay, now let's talk about how this deep learning is tried to be applied in polymer science. So there are mainly three kinds of the application of machine learning in material science. The first is, the easiest one is the characterization. It uses machine learning to classify material structure, detecting defects, or analyzing some scattering data is this belonging to this area. And then it's shown in the AlphaFold 2 is the prediction. So predicting physical properties, energy values, or the molecular structures, and those are belonging to this area. The hardest one is inverse design. So when you have this targeting output value and this generative model or some generative machine learning algorithms is used to design this new material or the processes. So let's take a look at examples for each cases. So here, using coarse grained simulation, the various sequenced copolymers are simulated, and from the simulation results, these three-dimensional feature maps are calculated, and that one is used to classify this aggregated structure and mapped into these latent spaces. So different types of aggregations are categorized. And in this example, these defects in lamella forming black polyethylene films, all different kinds of the defects are detected and classified using CNN-based network. So property prediction cases, the input of machine will be molecular structure or process condition, and output will be the property which is in concern. So various thermal and mechanical properties, and also the self-assembled structure in PISA cases will be in our concern. So this prediction, it also includes some of the earlier effort in polymer informatics, which is quantitative structure and property relationship. So in terms of that, this polymer genome is one of the platform which take the multi-scaled features in polymeric system, and using machine learning, it's not deep learning, it's classical machine learning, and find all the relation between these key features to the various polymer physical properties. So on this platform, if you type your polymer, then it generates this predicted physical quantities. So inverse design case, the input and output is now switched. So input will be desired properties, and output will be the molecular structure or the process conditions. So this inverse design has been actively investigated and applied in a new drug design, and even for the designing new synthetic route for organic compounds. It's a small organic compounds. And the work in the photovoltaics and the battery design, and also some variety kind of this solid state materials. However, this inverse design it's not that actively used in polymer designs. So the key concept of this inverse design is you need a generative model. So again, let me show here this variation or autoencoder, one of the generative model. So if you have certain polymer structure, and if you give this some of the conditional network for the property prediction, and then you train the network to generate a certain material which having this certain some given conditioned targeting properties. And of course, not only this deep learning network, some like a Bayesian sampling with sequential Monte Carlo, those kind of this optimization procedure can be also used for the inverse design. So machine learning applications for inorganic systems or small molecules are very active research field nowadays. However, this applying machine learning to polymers is more challenging issues. It's because these small molecules or these largely crystalline materials which has this small repeated unit cells, but polymers are embedded with structures spanning from like a sub-nanometers to micron or even more. So if one has these chemical details in repeated unit, but also the topological connectivity of those monomers and also the morphological complexities make all these parameter spaces in polymer systems makes more complicated, and also exploring this whole space is almost impossible. And furthermore, in a single bulk system, there is a variations in between polymer chain by chain in their molecular weights, or I mean, if it's some like random copolymer, then there's some monomer sequence could vary between chains, and all these raise difficulty in defining proper descriptor for polymer systems. So this plot shows a few of experimentally measured polymer properties which are taken from one of the large polymer database named PolyInfo. So different indexes means different polymers. As you can see here, even for the same type of the polymer, these physical quantities have some of the ranges of those values. So because these properties are affected not only by the choice of the system, but processing history and how the measurements are conducted are affecting these quantities. So that's why these existing polymer databases have only covered the limited scopes, and there's an issue of the accuracy and precision of this data set. And also if we want to build up the polymer data set, the fact that there are so many commercial product name, it makes this different nomenclature also make building the polymer database a little bit more challenging issues. So here's the list of polymer databases, which is taken from this review paper. And here the polymer genome I introduced, which is a platform, and PolyInfo, and so you can see the list of the databases. So in this society, there's some effort that trying to build up this polymer database, but still, as I mentioned, it's the numbers are still very limited, and none of the database providing this standardized and downloadable format of this data sets. To overcoming these challenges and make this machine learning in polymer science is more available, there's an effort. So the one option is generating this necessary database automatically, extracting the information from literatures, and that can reduce the burden for individual researchers. And also, to get some consensus in this society and try to build up the database, with common schema and standardized form. So this is in terms of the building the database. But at the same time, with this limited number of the data set, to make the machine learning technique work is one side of the effort. So the one is try to do the data augmentation or get some data from the simulation. And another thing is through having this better featureization or using some different learning algorithm to make the network can be trained with less number of the data sets. So in this work of detecting and classifying defects in polymer self-assembled images, when there's only 100 SEM images to train the network, the performance was less than 50%. However, by adapting this data augmentation, by flipping the images, and also combining these simulation data sets, the performance has raised more than 42%. So you can see that how the performance for each types of the defect. So this kind of approach shows that how this data augmentation and simulation assisted data set can help to apply this machine learning for polymer systems. So in this work, coarse-grained molecular simulations are used to generate the necessary data sets. So the polymers, which has these 10 different coarse-grained constitutional units, and the different sequence of this constitutional group makes different kinds of the polymers, and those are simulated. And these generated data sets are used to train the DNN network to predict the radius of gyrations. And here it shows the performance of this network. The polymer genome, this polymer property prediction platform that I mentioned earlier, they use this experimental data and the DFT calculation result, and using this classical machine learning algorithm named Gaussian process regression, they relate these polymers to the targeting properties. And for that step, they use these hierarchical descriptors. So from the atomic levels of the information and up to the molecular morphological characteristics, including the chain stiffness and branchings, are all used to as a polymer genome, these fingerprints. And to map these descriptors to targeting properties, they use this recursive feature elimination and only select the important features to associate these properties. So here it shows that, for example, to predict the dielectric constant, you need this atomic and QSPR level of the descriptors, which is in 35 dimensions. So finding a good molecular representation for deep learning network is also one of the open research problem. So there are many different representations. Like there's a way of encoding this molecule structure into the strings, and also the one of the back of the bondings and types of the molecules, or even the density field, electron density field maps. However, this considering the requirements that we want something which is invariant and unique, machine readable, and which is easy to compute, and moreover, considering the inverse design problem, we want this representation can be mapped into the continuous domain and invertible. So at this moment, people are still trying to find a better and better representation, not only for the polymers, even for the inorganic and the small molecules. So most famous molecular representation in computational chemistry is SMILES. And however, these days, these SMILES, the issues of the SMILES has been raised. So for example, in the toluene's case, so depending on where you start to convert this molecule into string, there's many different representation. And if you look at these two different molecules, they are very similar, except where these methyl groups are attached. However, the SMILE notations are very far away. And also, here's the SMILE notation for benzene. But if you make these changes in this string notation slightly, it makes these invalid molecules. And not only this one, because these branches are marked with these blankets, this incompleteness in this blanket notation and ring closure symbols. This can make many of the invalid structures. So to resolve these issues, there are many different grammars are suggested, and one of those are selfies. So selfie makes these grammatical rules only can generate the valid molecules. So here you can see that the mapping, the sampling on this latent space in VAE, the SMILE can still generate these blue invalid molecules, while the selfie maps generate only the valid molecules. However, selfie cannot yet fully represent the macromolecules, crystals, and the molecules with complicated bonds. So there's also different approaches. So rather than using this string, this SMILE string notation as it is, so using this, the list of the grammatical rules of generating this string SMILE notation as an input of the network after it is encoded. And also not only the string-based approach, there's also the graph-based approaches too. So all this molecule relation is represented as a graph, and all this the connectivity matrices are used for as a representation of this molecule. However, as you can guess, as the molecule gets more complicated, this computation load for this graphical representation is also increases. So there's one approach to make this coarse-grained approach. So these ring structures are represented one type of the vocabulary, and combining with these graphical notations, they showed some successful result of predictions. Of course, there's an effort to finding out the representation for polymers. These big SMILEs is SMILEs expanded to macromolecules. So it allows to represent this stochastic object in polymers. So for example, in this second cases, this red and blue, like marked with this curly blanket, represent these random copolymers with red and blue repeated units. And this allows to represent black copolymers and with lots of the branched polymers. And even the one with the networked structure can be represented using these big SMILEs. While this one is, in terms of the language-wise, it's rather complete and better for the polymers, but yet the real applications using these big SMILEs has not been demonstrated yet. So there's also an effort to using better learning algorithms. So here's an example of using active learning. So the concept of active learning is you start to read the small sets of the training data set. So here the goal of this problem is finding a pi conjugated peptide which result in a targeting self-assembled structure using this active learning process. So start from the small set of the simulation data set, and then do train the variational autoencoder. So reduce the dimension through this encoder, and in this, the sampling in this latent space is mapped into the finding the relation using this classical machine learning, this Gaussian process regression to measure the fitness function. So which means the self-assembled structure is how close to our targeting structure. And then based on this, using this acquisition function, they suggest the new sets of the peptide. And then the simulation for that peptide is conducted. And then now you have the more of the training data set, and repeat this cycle until the fitness function is saturated. And that's how one can suggest these new peptides for the targeting self-assembled structure. So to enable learning with less, there's another approach named transfer learning. So in this example, they use the database PolyInfo and QM9. And in there, there's physical quantities which have more data points are available. But while they are targeting physical quantities, thermal conductivity has only 28 data points. So instead of finding a prediction model for the thermal conductivity directly using this limited data set, they use the data for the other physical quantity with more data points, and they train the network for these physical quantities, and the trained network is transferred and retrained using this limited thermal conductivity data set. And this prediction networks performs better than directly finding a prediction model. And furthermore, they didn't use this network model, but using this prediction relation for the glass transition temperature and melting temperature. Using the Bayesian rules, this forward relation, trained forward relation, is used to find the inverse relation. And this sequenced string for this monomer, this S, they suggest the list of this molecule structures, and that one is further go to the screening, and they even go for the experimental validation of designing high thermal conductivity polymers. Okay, so let me summarize this lecture. So here we learn the basics on the machine learning. So what is the machine learning, what is the classical machine learning, and then I just show the examples of the supervised and unsupervised neural network, and what the learning process means with the backpropagation optimizers. And then in the next step, we went through how this machine learning can be used in polymer science, and then 3 different examples of the characterization, prediction, and inverse designs are introduced. And then also the challenges in applying this machine learning in polymer science are explained, and the approaches to resolving these issues using data augmentation or the simulation assisted approach, and finding a better polymer representation, or using some different learning techniques such as active and transfer learnings are explained in this lecture. Okay, so thank you for your attention, and if you have any question, you can email me, or you can try to ask me directly during the conference. Okay, thank you.